Lesson 5, Chapter 5, Part 1, we're going to be looking at thermodynamics. Thermodynamics is the study of energy, work, and heat. There are 3 laws of thermodynamics that you'll need to know. The first one being energy cannot be created or destroyed. It's only converted from one form to another. Second one, the universe spontaneously tends towards increased disorder. So another word for disorder that we use in chemistry is entropy. So entropy is a measure of randomness. So the second law is really just stating, I like to use the example of marbles. If you were to drop a bag of marbles onto the floor, what's going to happen? Are they going to fall and land in a perfect circle, or are they just going to go every which way randomly? They're going to go every which way randomly. So that is all number 2 is saying, is that the universe tends towards disorder. Things happen at random more often than perfectly. Number 3 states that a disorder of a pure crystal at 0K is 0. So when we talked about 0K before, 0K being Kelvin, 0 Kelvin was referred to as absolute zero because that was the coldest possible temperature anything could achieve. So they're saying at the coldest possible temperature, the lowest possible temperature, everything is completely frozen in place. So if everything is completely frozen in place, it makes sense that the disorder of a crystal would be 0. There is no disorder. Why? Because nothing can move. So everything is perfectly frozen in place. Now, why are these important? Because they're going to help us decide whether a chemical reaction is spontaneous or not. So we can figure out if a chemical reaction is spontaneous, or if it's not spontaneous, maybe it needs a catalyst or heat or other forms of help to get the reaction to move forward. Let's look at the first law of thermodynamics a little more closely and apply an equation to it. So the first law of thermodynamics stated that energy cannot be created or destroyed. It only changes from one form to another. So in this equation that we have shown here, we have delta E of the universe. So delta E, delta meaning change in. So anytime you see that little triangle, it means change in this course. So the change in the energy of the universe is going to equal 0. Why? Because we just said energy cannot be created or destroyed. So the total change in energy must equal 0. Now, the energy of the universe is split into 2 different types of energy. We have the energy of the system and the energy of the surroundings. So the system and the surroundings make up the energy of the universe. So what does the system mean? So energy of the system is the process under study. So for us, that's most often going to be a reaction. The reaction that we are observing, the reaction that we are doing is the system. The surroundings then are going to be everything else. So the surroundings are going to be the air around us, the temperature around us, the humidity in the air, anything around that reaction that could possibly affect that reaction. Since we set the change of energy of the universe equal to 0, that means that the change in energy of the system is going to equal the negative change in energy of the surroundings. So they are equal but opposite. Let's look at the change in energy of the system a little more closely. So remember, the energy of the system was the reaction, the test tube, the flask that we're focusing on. That includes the system. So we refer to this change in energy of the system as internal energy. So you'll see that word in a lot of the word problems when you're trying to solve for the change in energy of the system. They'll refer to it as internal energy. So the definition of internal energy is the energy of the system defined by both the kinetic and potential energies. So kinetic energy is moving energy, energy in motion. Potential energy is stored energy. So that would be, for instance, if you have a pencil or a pen on your desk. It has a certain amount of stored potential energy when it is not moving. Now, if you were to knock that pencil or pen off of your desk, that stored potential energy is now converted into moving energy as it's falling. So as it's falling, that potential energy now changes into kinetic or moving energy. So that's how those two energies are related. When we're calculating the internal energy of a system, we use the equation shown here. So delta E of the system is equal to Q plus W. So what do those variables stand for, Q and W? Well, Q is the heat energy going into the system. We often refer to it as thermal energy. And the W is going to stand for work. The units when we're solving for energy of the system are either going to be in joules or kilojoules. You'll notice since we have this prefix of kilo that this is a metric conversion factor. So we will convert it just how we convert any metric. So we saw on the previous slide that to calculate the change in energy of a system, we take the thermal energy or heat energy and add it to the work. So we're going to look now at how to calculate work. So the equation to calculate work is negative P delta V. So the P stands for pressure and the delta V stands for change in volume. Whenever you have change in something, you always take the final minus the initial. So we're going to be looking for the final volume and the initial volume, and we're going to subtract those two to get the change in the volume. Looking at the problem, it says to calculate the work required, and it wants the answer in joules. For 0.82 liters of liquid water to freeze at a constant pressure of 0.98 atm, expanding to a new volume of 1.01 liters. Notice it also gives us a conversion factor, where we can take 1 atm liter and convert it to joules. So let's make a list of our knowns, see what they have given us. So for the knowns, notice they give us two different volumes so that we can calculate the change in volume. They give us an initial volume of the water, which is 0.82 liters. Once the water freezes, as you know with water, when it freezes, it actually expands, so we get a new volume of 1.01 liters. So our final volume is 1.01, and our initial volume was 0.82. So we subtract those to get our delta V, or our change in volume. Notice we also have a pressure of 0.98 that we will be putting into the equation, and then we have our conversion factor that we'll use at the end. So plugging these values into the equation, remembering that negative sign that's in front of the P, so we have the negative sign on the outside. We add in the pressure of 0.98 atm, and then we subtract the final volume minus the initial volume to get the delta V. Then multiplying those two numbers together, we get negative 0.19 atm liter. Now we're not done because the final answer should be in joules, so we're going to use the conversion factor given to us to convert that atm liters to joules. Doing that, putting the atm liter portion on the bottom or in the denominator so that those units cancel. We take negative 0.19 times 101.3, and that will give us negative 19 with two significant figures, joules. So what does the negative 19 mean? Why is it important that we pay attention to whether it's negative or positive? Well, because whenever we have a negative value for work, that is telling us that work was done by the system. And we're going to explore exactly what that means on the next slide. So negative values for work means work was done by the system. So looking at heat versus work and what a positive heat value or a positive work value means versus negative. So let's explore heat first. So heat is seen as a temperature change. right? If the temperature is increasing, heat is being added. If the temperature is decreasing, heat is being taken away. So if the Q is positive, so if the heat is positive, that means that heat is entering the system from the surroundings. So we're looking at the top portions here. So Q greater than 1 or Q value positive, that means heat is going from the surroundings into the system. Now, if the heat is negative, so if you get a negative value for Q, that means heat is leaving the system. So it's going out of the system and into the surroundings. So this would be an example where you feel the flask heating up. It is releasing heat from the flask to the surroundings being your hand. Now looking at work. So work definition is the ability of a molecule to exert force. So if work is positive, so if it's a positive value, work is done on the system by the surroundings. So that means the surroundings is doing work onto the system being this white rectangle in the middle. Now, if work is negative, like it was in the example on the previous slide, that means work is being transferred out. So the system is doing work on the surroundings. Work is being done by the system onto the surroundings, going out. So one way I like to remember this is I think of the system as like your digestive system, like your stomach. Okay, so the surroundings being the food that you're going to put into your stomach and other things as well. So positive is when food goes into your system when you're eating. That's a positive effect, right? You're eating, it tastes yummy, food is going in. So you get positive values. Now, when the food leaves your system, however it does that, that is usually more negative experience, if you understand what I'm saying. So things transferring out of the system into the surroundings are associated with negative values, whereas things going into the system are associated with positive values. Let's look at a practice problem applying some of these concepts. So for this problem, we have a hot piece of copper dropped into a container with water. So you can imagine if this is happening, right? Copper is hot, the water is cooler. So what's going to happen is that hot piece of copper is going to warm the water around it, the water being its surroundings, and the copper itself is going to get colder. So the copper is losing heat, the water is gaining heat. More specifically, the water gains 465 joules of heat. And the water does 85 joules of work onto the copper. So it's asking what is the internal energy of the copper piece. So we need to use our knowledge to figure out if these values should be positive or negative. So looking at the first value, the surroundings being the water, so the surroundings are gaining 465 joules of heat, meaning that heat is being transferred from the system outward to the surroundings. So remember, when things are going out of the system, that's negative. So this 465 is going to be a negative value when we use it, because it's going from the system into the surroundings, the heat is. Now looking at this 85 joules, it's saying that the water does 85 joules of work onto the copper. So that means water being the surroundings. So surroundings is doing work to the system. So work is going from the outside into the system. So think of it like food going into the system. So if it's going in, it's positive. So the work in this case is a positive value. Now we can use that information to calculate the internal energy of the copper. So we decided that the heat was negative because it was going from the system into the surroundings. The work was positive because it's going from the surroundings into the system. So once you figure those values out, all you need to do to solve is add them together. Because the energy of the system is the heat plus the work. Heat is negative, work is positive. Adding them together, we get a total value of negative 380 joules. Notice it's out to two significant figures because 85 had two significant figures. Let's do another practice problem. Feel free to pause and try this one on your own to see if you can figure out if the joules given are supposed to be negative or positive before adding them together. So a gas is compressed with 128 joules of work being done on the system. The gas releases 275 joules of heat into the surroundings. What is the internal energy of the gas? Well, looking at the heat value of 275, it said that the heat went from the system to the surroundings. So if it's going from the system outward to the surroundings, it's going to be a negative value. So we get negative 275 for the heat. As for the work is going from the surroundings into the system. So whenever something goes into the system, we get a positive value. So the work is positive in this case. Next step is just adding those two values together. So we get negative 275 plus a positive 128 for a total of negative 147 joules. That is the total change in energy of the system. Now let's look at heat and how it applies to reaction equations. So for heat and reactions, there are two different types that we're going to look at: exothermic reactions and endothermic reactions. So exothermic reactions are when heat energy is released to the surroundings. So as you can guess, if heat is being released from the system into the surroundings, we are going to get a negative Q value, just like we saw previously. So the Q value is less than 0 or negative. And when we write it in a reaction equation, the heat is going to go on the product side. So the reason the heat is going on the product side is because when heat energy is released from the systems into the surroundings, we feel the flask get hotter because the surroundings would be our hand or the air around us, and the system is what's happening inside the flask. So when heat is released, heat is then one of the products. Looking at endothermic reactions, endothermic is going to be when heat is absorbed from the surroundings. So if heat is absorbed from the surroundings, so something is going from the surroundings to the system, we're going to get a positive Q value, as we've already seen. So when heat is absorbed, heat is going to be on the reactant side of the equation. Now, oftentimes, instead of seeing the word heat, you'll see a value here, so a numerical value in either joules or kilojoules, indicating that heat was added into the system from the surroundings. So this is most often when we need to apply heat to get the reaction to move forward. Now, if you were to be holding a test tube during an endothermic reaction, you would actually feel the test tube get colder. And the reason that it feels like it's getting colder is because that test tube is absorbing heat energy from your hand, because your hand is the surroundings. So when it absorbs that heat energy from your hand starts to feel colder. Enthalpy is represented by the variable H, capital H to be more specific. Enthalpy is defined as the heat stored in chemical bonds. So we're going to learn how to calculate the change in enthalpy. And remember, whenever we have change in something, it's represented by this triangle or this delta sign. And in this case, since it's change in enthalpy, it'll be represented by delta H, H standing for enthalpy. Whenever we have change in something, it's always final minus initial. So since we're talking about chemical reactions and chemical bonds, the final is going to be the products and the initial are the reactants. So whenever we're calculating the change in enthalpy, we want to take the enthalpy of the products, the final, minus the enthalpy of the reactants, the initial. Now, when we're calculating change in enthalpy, if the change in enthalpy is positive, that means it's an endothermic reaction. If the change in enthalpy is negative, that means it's an exothermic reaction. So very similar to those heat values, those Q values. If Q was positive, it was endothermic. If Q was negative, it was exothermic. So the same trend applies with enthalpy as well. Next, we're going to look at some enthalpy diagrams. You'll notice for both of these diagrams, below them are equations representing what is happening in these enthalpy diagrams. So you'll notice for the first one that we're going to look at, which is on the left, that the reactants are lower in energy than the products. When the reactants are lower in energy than the products, we're going to end up getting a positive delta H value. Whenever we have a positive delta H, as we saw on the previous slide, that indicates an endothermic reaction where heat is being absorbed from the surroundings into the system. Whenever we have an endothermic reaction, when we represent that in an equation, the heat is on the reactant side of the equation. Now going over to the other enthalpy diagram, you'll notice it's the opposite. So in this enthalpy diagram, the reactants are now higher in energy than the products. So if the reactants are higher in energy than the products, when we subtract them, which we have to do to figure out the delta H, we're going to end up getting a negative delta H because the reactant value is higher than the product value, giving us a negative change in enthalpy. Whenever we have a negative change in enthalpy, that indicates an exothermic reaction. And when we represent exothermic reactions in chemical equations, the heat shows up on the product side of the reaction. So we're kind of tying in together a lot of what we learned into these enthalpy diagrams. You will not have to draw the enthalpy diagram. You'll just need to be able to figure out, based off of an enthalpy diagram, whether the reaction is endothermic or exothermic. And you can figure that out by deciding if you're going to have a negative change in enthalpy or a positive. So let's do some practice problems, labeling the following as exothermic or endothermic, and giving the sign of the change in enthalpy, so whether it's positive or negative. So ice melting is going to be the first one. So if ice melts, that means that heat is going from the surroundings into the system, melting the ice. So if heat is going from the surroundings into the system, we should have a positive delta H being endothermic. And you can even think of this as well. If you're holding on to ice, ice is absorbing heat from your hand to melt it. So it's going to feel colder, endothermic. Next one, test tube giving off heat during a reaction. So I said if a test tube is giving off heat, that means heat is going from the system to the surroundings. So it's going to be exothermic. Exothermic corresponds to a negative delta H. Now, if the heat energy is positive, so this is that Q value. So if Q is positive, that's endothermic, and endothermic corresponds to a positive delta H. Now, based off of this reaction equation, figure out if it's endothermic or exothermic. So the deciding factor here is going to be the heat is one of the products. So remember, when heat is one of the products, that is indicative of an exothermic reaction, and exothermic reactions are going to have a negative delta H value. Dry ice vaporizing. So dry ice being carbon dioxide solid, so going from a solid to a gas phase. So in order for dry ice to go from a solid to a gas phase, heat needs to go into the system. So if heat is going into the system, we are getting a positive delta H, because it's going from the surroundings into the system, and that would be an endothermic. Water condensing. So water condensing is going to be an exothermic reaction with a negative delta H value. Next, we're going to look at the heat equation itself. So we've already talked about how to tell if a reaction is endothermic or exothermic based off of the Q value. So if the Q value is positive, it's endothermic. If the Q value is negative, it's exothermic. So now we're going to look at how to calculate Q. So to calculate Q, we use mc delta T. So M stands for mass, and when we're using it in this equation, it needs to be in grams. This C value stands for the specific heat. Now that C value you're going to get from a table, and it's going to be dependent upon the material that we're talking about. So there's different specific heats, whether you're talking about water, copper, aluminum, so it's going to be dependent upon what the material is made up of. Now the delta T part, remember delta means change in, so delta T will be change in temperature. When we're measuring change in temperature, we want to make sure that we're measuring in degrees Celsius, and that we want to make sure to take the final temperature minus the initial. That's very important, because if we get that wrong, our sign on our Q could be incorrect. And if the sign's incorrect, we won't be able to figure out accurately if it's endo or exothermic. So while we're talking about the heat equation is used when we use calorimetry. So calorimetry is one of the experiments we're going to be doing in lab. There's two different types of calorimeters that can be used. The one that we're going to use in class is the one off to the left. It's a constant pressure calorimeter. And when we use the calorimeter, what we're measuring is we're measuring mass and change in temperature. So we can use the mass and change in temperature to plug into the equation to calculate heat lost or heat gained. Next, we're going to look at specific heats. Specific heats being the C value in that heat equation. So the C value, the specific heat, is going to depend upon the type of substance that we're talking about in the problem. Why? Because different substances have different capacities to absorb a given amount of heat. The heat energy that is required to change the temperature of a substance by 1 degree Celsius. So if we're looking at the specific heat of water, for example, water has the highest specific heat capacity of all of the other substances on this table. What that means is that water has a very high capacity to absorb heat. So it takes a lot of heat to get water to change just 1 degree Celsius. Whereas if you look at iron, for example, or even copper, their specific heats are just a fraction of water. So since their specific heats are much smaller, what that means is it takes less heat to change the temperature of iron and copper than it does to change the temperature of water. So if you think about it, this kind of makes sense. For instance, when we're heating water on the stove, it takes forever to get the water to boil. However, we usually boil the water in a pan made of some type of metal, whether it be iron or copper or even aluminum. So the reason we heat water in these metal pans is because the metal pans' specific heats are relatively low. So those metal pans are going to heat up very, very quickly because it doesn't take a lot of heat to change their temperature. However, the water itself, it's going to take a lot of heat to change the water's temperature. So that's why it takes the water so much longer to heat up than it does the pan itself. Now, one other thing I want to point out are the units on specific heat. So if you look at the units are joules per gram degrees Celsius. Now, these units can help you remember what the units of all the other variables in the equation should be. So joules are the units for heat, for that Q value. Grams are the units for mass in the equation. And then degrees Celsius are the units for temperature. Let's look at a practice problem and how we're going to use this equation. So in this problem, we have a 329 gram sample of water, and they're cooling it from 52 degrees down to 22 degrees. Using the specific heat of water from the table, given here, how much heat is released? So what they're doing is they're asking you to calculate the Q value. So let's look at our knowns. We have the mass of water, 329 grams, and it's in the units we want, so we don't need to adjust. Remember, we need it in grams in this equation. They gave us the specific heat value, and then we have two temperatures. So it's our job to figure out what temperature is the initial and what temperature is the final. Because when we subtract them, we always want to subtract the initial from the final. So 22 minus 52 in this case. So our change in temp is actually going to be negative, it looks like. So when we calculate our change in temperature, we see it is indeed negative. So we get negative 30 degrees Celsius. Now let's plug those values into our heat equation. So we have our mass in grams multiplied by our specific heat multiplied by our change in temp. Notice when we do this, our grams are canceling, and so are our degrees Celsius. The only units left now are going to be J for joules. Looking at the significant figures, it looks like we only want 3 significant figures in our final answer. So we get an answer of negative 41300 joules. Now looking at this value, I can tell a lot of things from it. First off, the fact that it's negative tells me it's an exothermic reaction. Let's do another problem, this time rearranging the equation a little bit. So what would be the mass, so we're calculating M, for a sample of aluminum if 446 joules of heat is absorbed with a temperature change of 2.55 degrees Celsius. So they give us the specific heat of aluminum, so we have our C value. Notice for the temperature, they didn't give us two temperatures, so there's no subtraction needed. Instead, they already calculated the change in temperature for us, noting that it's a positive change in temperature. Now for the heat itself, it's saying that heat is absorbed into the system. So that means heat is going from the surroundings into the system. So this 446 joules is going to be a positive value. So writing our knowns here, we then want to rearrange the equation to solve for mass. So this is what it's going to look like when you rearrange the equation, because you're going to divide both sides by the specific heat in delta T, putting it in the denominator. Once you have the equation rearranged, you can plug in your values. 446 joules for the heat. As you can see that joules are canceling each other out. The 0.897 for the specific heat, and then the 2.55 degrees Celsius, showing that the degrees Celsius is also canceling. So only units left now are grams, which is good because we are solving for mass, which should be measured in grams. We want 3 significant figures, so we get an answer of 195 grams.